In a previous example, we looked at this cable structure that has an allowable force of 245 kips. That's the controlling factor. And that, coupled with the closing string that originates from the two endpoints of the cable, we are able to derive a form for the particular cable under this loading. So what I'm going to do here is turn this cable into an arch and show you the relationship between a cable and an arch as a funicular structure. So I'm actually going to use exactly the same loads here and the same positions, although considering that this will be an arch structure, the loads would be higher because an arch structure is under compression and these elements would need to be thicker to control buckling. So now that I've transferred those forces, I've got the same span and same loading condition here. And I've also flipped the direction and given it a 5-degree slope. And I just want to pause for a minute to look at this 5 degrees here, because if we take 5 degrees here, you should be comfortable with looking at slopes in both degrees and in rise over run. So it's a pretty straightforward calculation to turn degrees into rise over run, because we know the length that's given as 180 feet and the angle is 5 degrees. Taking the arctangent of 5 degrees, or taking the tangent of 5 degrees, multiplying that by 180, we get 15 3/4 feet. So that's 15 feet and 9 inches. So in terms of a rise over run situation, if we take 180 feet and divide that by 15.75 feet, we get about 11.43. So that's a little bit less than 1/12. So that means that we have a slope here of 1/11.43. So this is a number that you may want to commit to memory, because that says a 1/12 slope is slightly shallower than a 5-degree angle, but they are pretty darn close, and that's a good mnemonic to remember there. So next we also have to consider what's the maximum force that we can have here. So this is an arch cross-section. It's going to be 8 inches deep and 12 inches wide. And we're going to design for an allowable stress in the concrete we'll say that is 2,500 pounds per square inch. Now this F prime of C, that is how we designate the compression strength of concrete. F means stress, prime means the compression strength, and it's in compression, or prime is the allowable, the maximum. So the area here take 8 inches by 12 inches is 96 square inches. Stress is given by the equation force over area. Now, if we have an allowable stress and an area, that will give us an allowable force just by changing this equation. F times A is going to be equal to P. Therefore, we have 2,500 pounds per square inch times our area, 96 square inches, and we have 240,000 pounds, or 240 kips. That is going to be our controlling factor in shaping our structure. So next we need to draw a load line based on these lines. So this is all symmetric. Let's go ahead and put in our labels here. And O is representing, I'll draw it a little bit higher, O is representing the entire space below the deck here. So we have a series of loads of 24,000 pounds each. So we start out at point A. So I'm doing this at a 1 to 60 scale. That means that it's 60 kips for every inch. So this would be 40 right here. So 10, 20, 5, 4 is right about here. And then we continue on like that. So there is my load line. Now I want to bisect this load line into two parts because these are symmetric loads, equal loads, therefore the end reaction on each end is going to be the same, and we will have a closing string that parallels the slope of the deck. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We'll come in right here between E and F. And our closing string, again, the line that is parallel to the deck, bisects the left and right hand end reactions, and somewhere along this line we will find point O. Well, the governing factor is that we are allowed 240 kips. Based on this concrete strength and that cross-sectional area, we get 240 kips of allowable force. So in order to determine our line length, I'm going to take 240 kips right off of our scale right here, set my compass to 240 kips. If I swing a line from the top, I have an intersection point at this location. If I swing a line from the bottom, I have an intersection point here. This actually has to be the controlling factor because if I allow this one to control, we can see that it exceeds 240 kips on the bottom. It's going to be larger than that on the bottom. So my first intersection point has to be the controlling point. It's convenient to do that with a compass, but you can also do it with a straight edge. So here we see that it's 240 at this point. It's going to be a little bit less than this up here. Comes out to about 230. If I use 240 up here, it would be about 255 on the bottom, so we can't do that. So this is our pole point, point O. Now we draw rays from that pole point. And each of these rays represents the force in any given segment of the arch, and that segment will have the same angle as any of these rays. So let's start with perhaps E, just so we get the height below the deck approximately right. It doesn't really matter which one you start with. So that curvature is the arch form. Now, unlike a cable structure, an arch is going to have some thickness to it, where a cable is pretty darn thin. And what I'm drawing here are the struts that are going to carry the deck load down to the top of the arch from the deck above. And because the arch has some thickness to it, let's give that a little more thickness. The cable also, of course, has thickness, but it's quite small in comparison to its length. And there we have it. That is an arch that is shaped for maximum force down here of 240 kips. And let's just get out some other key lengths, or key magnitudes, I should say. So this is the furthest most on the left-hand side. That comes out to about 230 kips. That would be the segment here. And the maximum, of course, 240 kips is over here. And the minimum looks like it will be OE and OF. OE comes in at about 210 kips. I imagine OF is close, a little bit higher, about 215 kips. So all of these forces are in line with what we saw for the cable structure, but the form is much larger for an arch. That's because, once again, an arch is going to be subjected to buckling. That and the magnitude of the stress is far, far lower in the concrete in compression than the steel is in tension. But we can see that using this procedure, whether we do an arch or a cable, it's exactly the same process in form finding.